Hello everyone and welcome to the Victoria Game Engine series. In this episode we'll be tackling vectors and arrays. So now in the series I'm going to start introducing sort of like slideshows just as like a way to explain the concept beforehand so I don't feel like I'm tripping over myself when I'm creating the rest of the video. So the first question you might have is, well, what is a vector? And I've sort of written out here more or less what we do. So in this video, the idea of a vector and an array, which we will both be looking at, are effectively the same thing. They are a way to have a given number of bytes of data held in one location in memory. As it says there, the main difference between our two classes is that our vectors are designed to hold basically any type that exists in C++, but arrays will only hold variants, so we can have strings, we can have integers, we can have floats, we can have other arrays, we can have dictionaries, we can have, I guess you could have the other vectors, which I'll get onto, which I've mentioned there. You can have all these different types that exist in one thing, but for vectors, they will only be containing a single data type, but of course, as it says, arrays use multiple ones. So I also wanted to outline what this class is going to do, and effectively what we need it to do is we need it to have two main functions. It needs to, one, be able to access the operators. It needs to be able to append, push, pop, do all those sorts of actions. You need to be able to resize it in case you want to, have a bunch of data types at one place. You need to be able to clear it. You need to get rid of all the entries. You need to be able to search for items within the vector. And you need to have iterators, which I'll also get onto in a bit. So all of these methods that we will be creating, we'll also have extra methods. Most notably, we'll be having ways to assign the values in a vector from one to the other. We also have operator overloading in this video, but for the most part, we will just be focusing on sort of our functions and making them the vectors functional. So this was another question that I had at the end of the last video. Someone asked, why don't we use std variant when we're creating our variant type for that video? In short, it's very easy to use something like std vector and std variant when you're starting out in a project or having a very quick project that you just need to get something up and running rather than have like a long-term code base to exist. But in our case, we want to be having these tools because we want to be able to manage our own, know what the methods do, debug them if something goes wrong, so we know when it's our problem rather than a usage problem. And yeah, that's pretty much everything. So without further ado, I think it's time to just hop into the code. Before we do any actual writing of new code today, I just want to go over a couple of changes and additions that I've made prior to making this so that we can facilitate the new changes that we've going to cover in this video. So the first one is in our typedefs.h. We have added some extra things to our inlining of variables. So the first thing that we're doing is that we are now checking if debug is not defined. So if we are running in a release build, then the force inline will get either compiled to this or to this. And I believe I was just leaving this as inline in our non-defined versions, so that will now be corrected. And lastly, for our force inline, when we're in a debug build, we're just going to have it say inline. The reason that we have it set up this way is because when we're debugging our code, we want to be able to debug it when we're in a debug build, but when in release, we're not going to need that, and so we're going to want a force inline to save a little bit of space there, especially when it comes down to actually being able to debug it, which you can't normally do with the setup we currently have. Aside from that, we also have a addition to our file of error conditions, and we just have an out of bounds fatal. Because we are going to be dealing with vectors and arrays, of course, we are going to need to be able to throw a flag whenever a fatal out of bounds error occurs. So that is why we have this here. And I've written out a quick explanation of these. And a note on documentation, I'm currently going through on my own copy of this and updating everything to have detailed notes. So I will probably go through at some point soon and update everything to have some comments added to it so you can, of course, read it for yourself and understand what's going on. One thing that we need to do before we can start writing our vector and array type is something that I thought would be good to talk about and just mention a little less off chance is we need to create a static allocator class, or basically a memory class that we can use to statically allocate and deallocate memory when we need to. So we're going to be creating this under the OS folder. This will be where everything sort of related to our operating system will go. So if we're talking about audio, if we're talking about, you know, our base OS for running OS specific code, if we're talking about displays and windowings, all of that will be going under our OS class. And under here, we're going to be creating a file called StaticAllocator.h. And all we need to do is I'm, again, pasting in. And here we have a whole bunch of allocation commands. So we have, first off, we have just an allocate, a reallocate, and a free, and then zeroing, setting, and copying in memory. Now, these are just going to be wrappers for standard library. So the standard C words of malloc, realloc, free. But we are making it in this way so that we actually have an include that we could in the future add tracking to and make sure that allocations are being tracked rather than just blindly allocating every time. So under our OS folder, again, we're going to be creating our StaticAllocator.c++. And for those of you who have probably figured out what it's going to look like, it is going to be very similar to the last one. 2 standard library includes here, that's for stdlib and string. And all we have is malloc, realloc, free, memset, memcopy. Zeroing out is important for some blocks of memory, specifically ones that we will want to read a value from or set a value from, and it needs to be set to 0 by default. And so we do this, so by default everything is set to null in case of anything that could happen in that instance. This really is just a wrapper class at the moment, but in the future we can add functionality to it, which is why we have written it this way for now, because there are other things that we can add, like aligning memory and tracking it so that we can say how many bytes of memory we've used at a given point, rather than having to do some other magic with the OS that we may not want to do. So now we actually get onto the actual content of today's episode, and we're going to be starting out with creating a new folder called data. And under data, we are going to be creating a vector.h file. One thing that we should note about the vector class is that it's going to be header only and everything is going to be inlined. This saves a little bit of time with compiling because this class will just get inserted wherever it needs to be used, rather than having this class sort of exist but it needs to be compiled against, and that can slow things down. So we have this as a header library, header only file instead, just to keep that from ever having problems. So again, I'm going to paste in, and we're just going to explain everything from the top. So here at first, we just have our sort of explanation of the class as a whole. I believe I recently went through and did some documentation on most of the functions. So pretty much all of these should have some documentation to it anyway, as you can tell by this very long line I've made here. So taking it from the top of the file, we have our include. So we're always going to need our type defs. We're also going to want some error macros. We're also going to want our static allocator, because we will be working off a pointer type, and because we're using a pointer, we need to keep allocating and reallocating memory to it in a lot of situations. So, of course, we're going to need to have our allocator for that, of course. We are also going to be including this standard library include, which is a C++ exclusive standard library include. This is for lists, and we will get further down, you'll see where that is actually used. Something I also forgot to mention, I kind of talked about it at the start with why this is header only, but another thing that I forgot, which is probably really shouldn't have forgotten, template classes like this one, which always takes a type name of T. So this can be any data type. So that can be like an int, that can be a car, that can be, when we get our string library, that could be a variant. It can be all sorts of things. Because it's just asking for a type name. So it's a very broadly applicable class and can be used in pretty much every data type that you'll be generally dealing with. But because it's a template class, that means that we can only use it in a header file as well. So this code can't be compiled because, or at least it can't be compiled in the way we normally would. You have to keep type names in the header files. And because all of the functions here will use the template at some point, then we just keep all of it here as is. Actually explaining the class now, we have some private variables. These are just some data that we can keep hold of. So we have the uint8, which is the size of the data that we are currently storing, which is set at a bunch of points when it's relevant. This is just so that we have a number that we can just look up rather than constantly going against size of. We also have an element count and a size. So the size is the number of bytes that the array or the vector takes up. This is probably the most important tracking number because we want to know how many bytes we've allocated, how many more bytes we might need to allocate. This number is more for lookup purposes. So if we look at our element count being, say, 3, rather than taking the size and dividing by the data size, because we always keep count of how many elements we have in the array vector, that will always be set. And lastly here, we just have a pointer to something of type t, which is by default set to null pointer. And this makes up our block of memory that all of our values are going to be held in. The first two functions that we have coming up then are our getter and setter functions. So the getter function does a fatal lookup to see if we are, actually inside the bounds. And if it is, it'll throw an error so we can see where in our code we've called that and been an idiot. But otherwise, it will just turn the item at the given index. We also do the same sort of thing here. I did add a thing here that said something about problems. This was something that was resolved. You can sort of ignore this, but it does detail some of the problems that I was having with some of our assignment issues that I can get into data. So further on there, we have some definitions for ref and unref functions. If you're used to Godot, you've probably seen these. And I will note that these are very useful functions. So what ref and unref will do, ref will reference from a vector. So the one we have here, we have another vector that we are assigning our type to. And we take the vector we want to assign from to copy over all our data, which needs to be done in a certain way. And our unref function is basically our clearing function. It just sets all of our array size to 0. It has nothing in it. It is considered empty. Frees everything, so it's either A, ready to get thrown away if it leaves scope, or B, if it needs to be reassigned, which you'll see in a bit. And one of the really important functions that we want to keep an eye on, which is our resize. So this will take a new size that we want to resize it to, and because this data type already has its old size, its old element count, and its current data size in it, it will always be able to keep those to hand. And because it doesn't actually return any memory or anything, we just return a type error that we can then look up error messages if that fails, of course. So here we have an interesting struct that you might not have come across, which is an iterator struct. These exist so that in C++, you can define a for loop like for const int I in, say, a vector, and say vector's an array of integers. You can assign for loops like this, and this iterator structure will just look to see, okay, so what's the first point in the array and what's the last point in the array, and we'll iterate through all the values there. So we have to have all of these definitions created so that we can do that in this structure, which is returned to us by our begin and end operators here that are the default functions that a iterator class will look for. And below that, we have a couple of similar functions. So we have two sort of access operators. This is the brackets that you're used to. So we have, say, a vector of, say, vec, and we want to go 3. So we want the 4th item in. Then we can retrieve it that way. And there are two versions of this. They do basically the same thing, but one of them is constant and the other one is non-constant. Or this one is constant and that one is not constant. And this is just designed so that the type it returns here, while it is of the similar place in memory, you can't actually modify what that value is and return that in because it wants a const only. Then we have a equals operator. Again, what this does is this just assigns one vector to another. We manually copy over our data size because I was having issues originally with data size not transferring because of allocation issues. So we do that manually now. We have two equivalence operators, one to say it's equal to, one to say it's not equal to. We also have a good few sort of quick helper methods. So we have a size method, which returns a number of elements. We have an isEmpty method, which returns if the element count is 0 and if it's got no items in it. We also have pointer size, which actually returns the number of bytes, so how big the vector is in memory, rather than how many elements it contains. I also have a note that some of these could be unsafe, but we do need a pointer. We have PTRW and PTR. These are also similar because I ended up using these in other places. And what this does is it just returns a pointer, so the actual pointer of data that you could write to, and it also returns a constant version that you cannot write to in case that you need to pass that to a function that you want it to not be changing the data in it. Below that, we have a few sort of helper methods. These are our real extra helper methods that might be changed in how many that we have at some point. We have append, remove at, insert at. We have push front, push back, and pop back. We have clear and find. Again, you probably know what these do. Pushing and popping from the front, so that's just getting and retrieving items from the front. Pushing and popping from the back, same thing, but from the end. Clearing removes all the entries. Find gets the index that an item is at. And again, we will go into more depth when we get to those functions. Below this, we also have some class constructors. So the first one we have is just an empty vector. By default, this will always set data size because this by default is set to 0. And if you started referencing things or resizing instantly, you would end up getting divide by 0 errors because the data size was set to 0. We also have a default vector class constructor to create from another vector. And we have a third constructor that is using an initializer list. I'll explain this very briefly. So in C++, you will normally you can have an array that you can set. So let's say we want an int array of 5, which is equal to like 1, 2, 3, 4, 5, right? And what this does is is an std initializer list means that I can say I want a vector of type int array, and when it creates a type vector to assign this into, it will use this list, which is an initializer list, that to look all the values up from to put those into our vector type. So this is transferring from raw C++ into our higher level API effectively. And all that does is it just takes the resize, it takes the data size, it resizes itself to be the actual data size it wants, sets the element count to 0, iterates over, so it adds every element manually, and then does this weird assignment here that doesn't really need to exist. And the last thing that we have, of course, in our class is our class destructor, which effectively just does unref and removes all references that we have to it. So that's actually all of the methods that we have discussed as a baseline for what they are and what you can broadly expect them to do. Now we can actually dive into the details of what really happens. So the first function that we're going to be looking at in this instance is our ref function. And the first thing it does is it needs to do a couple of things. The first thing it does is it does a quick check to make sure that the pointer that we're trying to copy from is not the exact same, because if it is the exact same, there is no point trying to copy the data, so we might as well just boot out of the function so that we don't end up wasting a bunch of CPU time doing something that doesn't need to be done. Then we call to unref, which again I'll explain a little a little bit later to just clean everything up, and it sets our pointer to equal null pointer, just so that any memory reads that we might have don't mess up. And then we check if the other vector's pointer is null, and if at this point that is the case, then there is also no point copying from this because there are no values to copy from, so we boot out. We then also call to error to see if we get an error from our resize. Realistically, the only thing that can happen here is if the resize fails because we're out of memory, and in that case, that will be something that gets flagged, and of course we can investigate at that point. Now, I do have a very long comment here as well about what this does and why we're doing this, but I'll try to go off my own words on this and what it does. So the thing that we first check for here is we check for std is trivially copyable value. What this does is this is another thing from list. And what that means is if the type is easy to set in memory, so let's say it's just an integer, right? If it's an integer, then you can just trivially copy it from one piece of memory to the other. And if that does happen, then all we do is we just call to our StaticAllocator to then manually copy one. So the StaticAllocator will manually copy all of the data from the other pointer into our pointer and set the size properly so that all of the memory does what it's expected to do. However, if the data isn't trivially copyable, so for every item, and realistically this should be p other or p from, it will create a new instance of that at the point t. And what it does here is it has a for loop. So for every element in the old vector or in the new vector that we're copying from, we want to create a new version of that type at a given point. And we use that saying the memory address of the pointer at given index, assigning it to a type of type t, copying in from an instance of that at the other pointer at a given index. And that's basically what this does. This is sort of placement new, which just places a newly allocated item at a given point in memory. Next up, we have our unref function. The first thing that this function does is it just double checks to see if the pointer is already null. If it is, then we don't actually need to do anything. And again, it also now it checks again to a similar sort of namespace, but rather than checking if the item is trivially copyable, it now checks if it's trivially destructible. If it's not trivially destructible, then that means that we can't just get rid of it because it's probably holding on to memory or it's holding on to other types that hold on to memory. So, of course, we need to do something about that. And the first thing that we do is we just grab the current size, which is the number of elements. And for every element in our array, we get its memory address and we call its destructor. That's all that does. This fairly self-explanatory what we need to do. And we do this because there are some parts of memory that need to be destructed because otherwise they will throw a whole fit when they're freed. And once we do that, we call to the StaticAllocator to then free all the memory that we have assigned, of course, assuming that we have it has been assigned at this point, which generally should always happen because by default, our pointer will only be assigned when we use resize, and resize will always allocate memory. Speaking of which, we are now moving on to resize. This is it's a decently lengthy method. There's a good few lines in this one. So the first thing that we do in resize is before we actually start doing anything, we just want to double check if our new size is less than 0. If it's less than 0, we can't allocate how much memory it is. So we're just going to throw an invalid parameter there and just say, yeah, very funny, mate, leave. Next up, we manually set our data size. Again, I added a comment here to say, if we're using an allocator and we zero out the memory, it will set data size to 0 when it's not. So what we need to do is we need to set that to be size t whenever we need to look it up. We also want to save a couple of variables. So we look at our current size. So the number of, so before we resize anything and change any values, what the current size of our pointer is. And also we want to get the new element count so that we can check to see if, any of the elements have changed. And first up, we want to just double check, okay, if the current size is the same as the new size. So if we don't actually need to resize it, then there's no need to change anything. So we'll just boot out. If the new size is set to 0, we automatically assume that we want to free all the memory and get rid of it. And so in that case, we will just return OK as well, and we'll boot out early. Otherwise, we are assuming that we actually want to be adding or removing elements from the array in some capacity. So this is where we go to next. So if the current size is less than the new size, i.e. we want to add more elements into our vector, then this is the first set of instructions that will go along. So if the current size is set to 0, then we haven't allocated any memory. And so by default, we will say to the static allocator to allocate a number of given bytes. And that'll simply is all it does. Otherwise, we double check to see. We also do a similar thing here where we reallocate. So we just simply, reallocate a new number of bytes. And then we do have a little safety check here. Realistically, that should also be here, so I might go and update that. But that just double checks that the new data is, can be held in memory. And if it can't, it'll boot out saying it's out of memory. And otherwise, we just assign over the new data manually. Now, normally that would be the point where we can just wrap it up and go home. But of course, we do actually need to do a little bit more double checking. The first thing that we do is we want to check if the class that we're currently dealing with is not trivially constructible. What that means is that it can't just be placed in memory. It has to have certain things set up. It has to have, class constructors called so that things can get allocated a certain way. And here we call for I being set to the current size of the pointer divided by the data size. Really, that should be current size. I don't know why it's like that. Again, I might edit that. And I is less than the element count, and we are incrementing I. We then allocate a new placement of a type pointer at a given index of class T. And otherwise, the data that we're dealing with, it will just get zeroed out. And the last thing we do at every point there is that we just assume that everything's gone well. So we set our new size to be the size that we want. Otherwise, if the current size of the array is bigger than is the new size, that means we want to get rid of some elements and we need to destroy them somehow. Because we can't just clear the array because not every element will want to be cleared. First off, we want to double check if it's trivially destructible. We've been through this. If it is, then we can just go ahead and reallocate and ignore it anyway. But if it isn't, then we need to do some extra things here. So for instance, we call to I to be our new size. I is less than the current size, and I is being incremented. We then get a reference to T, and then we destruct it, and we call its destructor, and then we delete it, calling delete. Because normally when we create our new items, if it's not trivially copyable or if it's constructible, like here, then we need to make sure that its delete is being called appropriately. Otherwise, we can just go ahead and reallocate it so we can get all of our bytes into the array. Again, we double check to see if it's null, and if it is null, that implies that we're out of memory, so we boot out. And then we just set the variables manually. And because both of these processes at this point should be fine, we also manually set our element count to be our new element count. And that's the 3 main operations out of the way. So now we can focus on a couple of the the ones that are based on searching. So the first thing that we have here is we have our equivalence operator. So if 2 vectors are equal to one another. So we have a const int of s. So we get the size of the array. If that size is not equal to the other size, then by default we'll automatically return false because we know that they're different sizes. 2 arrays of different sizes are not going to be the same. Let's return. And then for every item in the array, if the pointer at a given index is not equal to the other's the other item at the given index, so if these two values don't align, then by default it's already going to be wrong and we're just going to return false automatically. But if it makes it through that process, then we can assume that by default it's going to be true anyway. And we also have the operator not equal, which just returns the opposite of if this returns being equal. Append is quite literally just another word for push back, but we have both of them in case someone wants to use them. So we just have it set this way. Remove at is a bit of an interesting function, just generally I find in the way that it's been written, just because to me it seems really ridiculous in how I've programmed it, but to be honest, I think it more or less works. So the first thing it checks is if the item it's trying to remove from a valid index is greater than the current index or less than the current index. And if that's the case, then we just boot out anyway. And then the first thing that we get is that we get our less than. So that's the number of items less than the index we're looking at, which normally would just be the element count at that point -1. But because of indexes starting from 0, we can say, okay, so we can just say it's from the current index we're looking at. We also set up a lesser array. So this is a vector within a vector that takes all of the items that are less than the given index and appends them in. We also do the same thing for the greater array. So this looks at everything past the given index and 1 and is less than the element count and appends those into the array. And the new size is set to be the element count -1 times the data size. Then we resize the array, and of course if that ever has anything fail, then it just boots out. And then we have a bunch of conditions that we can look at. So for every item in the current array -1, we are going to be looking at whether to remove it or not. So if the element count is 1, by default, we're assuming that we just want to clear the array. So we just call to clear, and then we break. We don't want to do any of the other processing because that's not going to work. We just want to get rid of the last item out of the array. If the smaller array size is 0, then we can just automatically keep assigning the pointer to whatever is in the greater array. And the same thing with the greater array. These are basically push and pop. There's a pop from the front or the back. They will just keep doing this. And at this point, this is the reassignment, which will get overwritten, which maybe I should reprogram this for actually treating more complex values. And at this point, then we are actually reaching everything that we actually want to be looking out for. So if I is less than or equal to the less than -1, then the pointer at then index, the given index should equal to that of the lesser array. Otherwise, then we should be looking at assigning from the greater array at the index of I minus less than, hence this weird operation. And that will just reassign all of the elements into the array at a given point because it saves all of the information outside of the array, resizes it down, and then just moves everything down the array by a given amount to make up for that. Then we have an insert at function, which kind of does the same thing. So the first thing we do here is when we're inserting, we want to double check that the data size isn't 0, because if it is, then this function here will fail. So just set the data size if it isn't. And again, another fail condition if resize isn't okay. And then for everything, I is the size -1, I is the size of the array -1, I is greater than the current index that we want to insert it at. And we're going to decrement I. We reassign from pointer I to be the one below that. And then at the end, once that's moved every item above a certain point out of the way, we then take the pointer to a given index and assign that to item. Then we have some push and pop front. As you can tell, this just inserts an item at the first point in the array. This gets an item at the first point, or again at the first point in the array, and then removes it, but still keeps a copy of the item and returns that. Pushback and popback kind of do the same thing, where if the data size is set to 0, then we set it manually because we're adding data size here. And then this just, again, calls to the resize function. And again, there's another error fail condition here if resize fails. And then we manually set the item at the given index to be equal to that, which is a little bit different, might change it up. And then popback kind of does the same thing where it just gets, that really should be get actually. And I don't know why it's doing that, because that is most certainly, okay, that's a weird error. That is most certainly not how you would write the popback. So that should be get p element count -1, as is set there. That's weird. And then it just returns the item. So those are basically the same, just where they're getting the items from is different. Okay, last couple functions here. So next up we have our clear. This sets this calls resize to 0. When we saw what that does, that calls unref and sets the data size to 0. And this also sets the element count and the size in bytes to 0, so that we also can make sure that our is empty flags still flag properly. And then we look for our find function. This just takes a copy of item and just checks for every item inside the pointer to see if it's equal to that item. And if it is, we return the index. And if it is not, it will return -1 by default to say, okay, we couldn't find the item in it. Please deal with it your own way. And then we have our vector constructor and our destructor. So our data size is manually set here, and then we call to ref to, do everything that ref does from our other array. And our destructor, again, unreferences and destroys everything that we don't need, mainly clearing it and just cleaning out everything in the array, as we would hope to do when we need to get rid of the type. And that is pretty much the entire data type explained. I know there are a couple of errors in there, and that's sort of on me. I don't think I've kept very consistent with everything I've done. Some of these are pretty hacky changes, especially that remove at function. I feel like this could definitely be improved somehow, which I may look at, but again, we're going to stick with this for now. And sticking with things, we are now actually going to move on to the other type that I mentioned. Of course, that is our array type. As I said earlier, it's going to be created in our variant folder. So I'm going to create a new file and call it array.h. And as I paste this in here, you'll see that it looks very similar to our vector, just without all of the comments and, of course, without all of the template stuff. And again, there's not really that much to explain here. We still have, our ref and unref functions. We have our iterators. We have our these operators, assignments, equivalents, all of the same sort of operators that we had before. There's not a lot of point really explaining some of these, because these are mostly the same that we've seen before, but a couple that are unique to this I will go over very briefly. But of course, you're going to want a source file, because a lot of these are going to be compiled, unlike our friends, the vector file. So with our source file, we're just going to copy and paste this in again, and I'll just try to go through everything that has actually changed. The very first thing to note is our array data class. This is probably best off being a struct, but I'm keeping it as a class for now. And it is mentioned here. These are our incomplete types. Why do we have these here, you may ask? Well, the reason that we have these here is because you can't because we want to include the array header file in the variance header file, but if we were to have the full variant class, we would include the variance header file. You end up in this lit circular dependency that you can't really get out of. So what we do instead is we just forward declare a variant here, and we forward declare our array data here, so that when we implement the methods themselves, we can treat them as you normally would. So array data is just the internal data of the array without mentioning like variants, which you can't have incomplete types of without having the header file anyway. And that's why that's there, basically. The mutable data here, the reason we have this set as mutable is so that we could just raw assign two pointers across one another without having to like copy them. And that's why that exists as is. But I will go into this file and I will now explain. So we have one thing, we have our array, which is, of course, of type vector variant, as I mentioned a couple times. We also have two booleans. We have a read-only boolean and a freed boolean. The read-only is so if we want to create an array that we just only read items from, so it can't be like written to. If you want that in your code, then you can set that, and then you can have that as you will. We also have this bool freed, which I've noticed as a hack, because I'll admit to you guys, the first time I recorded this video, I had put everything together, not really tested out variants and arrays and them assigning one another. And I had the biggest headache trying to get this to work until I realized that there was a very simple problem that I was facing with the array data class and how it was being treated. And this very simple fix here has saved me a lot of work. The other thing we have is a ref function. This will look pretty much the exact same as our other type. So we have a from a data, and then we just create our own here, check if it's null. If they're the same, return, of course, unreference everything, and then assign them. Very self-explanatory, and again, very similar here. If our data is null pointer, don't do anything. If our data has already been freed but has not been set to null pointer, then we do that and then return. That prevents this delete giving a free base error that can happen sometimes. If it's already been freed somewhere else in memory, but we want to free it here, then we set that here. Now, again, this comes back to this comment here. Realistically, we should not be having it freed on the first instance and then try to be accessed on another instance. That really should not be happening. But this was simply to get this class up and running. Realistically, I should be replacing it with something like, as I mentioned here, Godot's ref counted, which for those who are unaware, of course, realizing maybe should explain what that is. A ref counted object just keeps a list of the number of times that your object, item, whatever, has been referenced somewhere else in the application. And every time you increment that ref counted, it will keep a number of different references. And in the case of things being freed or allocated, when that ref count equals 0, at that point, there is no other object that is still using this piece of data, so you can free it. And by default, we'd probably want a system like that, where you can see, okay, this object's still in use, don't free it. Oh, we're trying to free the object now, it is in use. It isn't in use, we can free it now. That's sort of why this exists. But to get this class up and running, we can do it this way. And we will probably come back to something like a ref counted later on in the series. I kind of just had a moment with this, but I do delete the data and then set free to be true and set the data to be null pointer. Somehow that works. I don't know why, but you can still assign the values and say that it's been freed somehow. And, you know, it actually does free it. It actually does delete the data, and that all works. We also, again, have another iterator class, which does the same sort of thing. And it takes the pointer and the pointer plus the array size. We also have access, which is just the same sort of thing, using the same operators. If these are the same, then we return, otherwise we reference. And we also have an is equal operator rather than using the operator symbol here, which we may change in our vector class later on. Size, is empty, is read-only, set read-only, and all of these are pretty much as they were here, except that is read-only and set read-only are interchangeable. And you can see that they are set up that way here. We also have append, so it takes an item and pushes it to the back. We also have some modifiers here. And as you can tell, we have a remove at function, and the remove at function will send a message saying that you can't remove from an empty array, and you can't add or remove from an empty array, and you also can't do anything from a read-only array, which is important for this. And otherwise, if those two fail, then we remove at or insert at, and we basically have the same thing that we saw in the earlier file with here, and again with variants being returned that will set as null as well. And most of this, again, it's literally just wrapper functions. We also have here, we have a little for loop, I guess. This is just because fill is something that we could do that we probably don't want to do in our vector type because there's no need to set every instance of something in a vector. But that will just fill the variant with something of one type in case you want to do that for whatever reason. I personally don't have a reason that I can think of doing anything like this, but the option is there, of course. And the only actual function here that is sort of an extension of what we have here is our equal function. And it just says, if the data's other data, if they're the same, then yeah, it's going to be equal. Otherwise, we get a reference to the data's array and the vector variants, and just do this instead of comparing array datas. Set the size to be the size to a1's.size, and if the size is not the same, if these two sizes aren't the same, then it's false. And of course, if we call to the index of a1's hash compare function, so again we are dealing with two types being different, and if these two types are not the same, then we return false, but otherwise we return true. So very similar to the equivalence operator in our vector type, but it's changed up slightly to accommodate for how arrays are held. And when we construct the array, we also manually set our data to be null pointer, and we manually set it to be, and then we reference it as we would. And here, I do make a kind of note here about assigning arrays. So when we create a new empty array, we will always be copying from a new array data. So there's no other constructors aside from, but an array p from will assume that an empty array has already been used so that we can assign the new array data here. And we don't have any parenthesis because it's just a type and it doesn't have any constructors, so there's no need to call a constructor there. And then the destructor, again, it just removes everything from the array and then just deletes it from memory. So that is most of the array class done, but there are a couple more things that we need to do in the class that are actually in our variant. So let's head over there and let's start off from the absolute base we're going from. So the first thing that we'll do is we're going to add a couple of extra operators here. So when we're dealing with an array, in this case, in the case of actually having these in the source file, because our variant was an incomplete type, we couldn't actually use the operators there. We would have to do it in this part of the file. So we do that here, as you can see. And it's just pointers or dereference pointers, just getting the raw pointer, increment and decrement, and those are now all added. We're also going to want to go and grab the an include for our array. And we're going to add the array as a type that we can use. We are also going to want to add it to our list of variables that can. So we're going to add it to our list of booleans for things that do need to be freed, and because its type does actually need to be worked with, then yes, we need it to be freed, and it will call to clear internals. We will also be adding it as a variant constructor, as we can see there. And now we need to go into our source file to change a few of these here, because as you would expect, there's a whole bunch of new things that we need to add here. So the first thing we need to do is we actually need to go to our clear internals and add a destructor here for that. So we'll call to the case array, because if you'll remember, by default, the only case that we'll ever deal with from before is just atomic types, but now we actually have types that do need to be dealt with properly. So we will be adding these as those need to be added. And we'll call to a reinterpret cast of type array pointer. and that'll be typecasting our memory from that, and we'll be calling the destructor for the array. So reinterpret cast takes the memory, so our 16 bytes of memory that we have, and casts it from being just eight general bytes into being a pointer to an array, and then we can use that to call its destructors, and we destruct that given array from wherever it's being held at the moment. And of course here you call to break. Now that's that function done. Next up is in our equals operator, and that's just going to be a case of array, and all we'll be doing here is a little bit of this. We will dereference a reinterpret cast, and we will assign it as an equals operator, so the creation of those two will then be held with by our array's own operator assignment, so that we don't actually have to do any custom programming there. You also have our hash compare function. This, again, is going to be much like the one that we just created. It will take a type of const array, the left and the right, so our data and the other's data. And if those are not equal, then we'll return false. Otherwise, we will return true. Realistically, this should just be a return L is equal, but I'll keep it as is for now. You can change that if you want. Most of the operators here don't really need anything to be added, because by default we haven't supported any of these yet. Most of those will be coming once we add a string library or anything we want to there. However, at the end, we are going to want to add our constructor for a variant as an array, as we will see here. And what that does is it takes a dereferenced cast and assigns it to the array that we're currently dealing with. So it will just take that and it will just assign that as basically what is a pointer. So the one thing to note about this is that rather than assigning it just as an array and it's held in the variant itself, the variant is just holding a pointer to that array type, which is why we would end up with the double free problem as seen earlier. We probably will look very soon, realizing now what's actually going on. We will probably want to look very soon at changing this here, this freed, so that it's actually reference counted, so that we don't end up with the problems of arrays being freed before they're actually used and problems just arising from that. But now that we're done there, we can actually, that is actually all of the code that we need to write for this episode, I believe. And now we can give a little bit of a test of the wheels. So what we're going to do is we're going to include from our variant folder, we are going to include an array. And we are also, just to prove that this is working, going to include from the vector as well. Another thing I think I just glossed over really quickly, we do actually include vector and variant in our array in our array source file, just so that these work. And we are going to write a little test. So in order to show that arrays and vectors can work, the first thing that we'll want to do is we'll want to create an array that can do some things. So we'll call this array y, and we're going to append a whole bunch of things. So let's append 1. Let's just append 2.2. And let's append, true, right? At this point, these are all the data types that we could include. And to avoid any problems, we could also append y to itself because it's an array, but I won't do that because I don't want to deal with that right now. But to show that this really is working, we should then be able to say x equals y. And that will assign the type. And that will show to us that our array is capable of being able to be reassigned to a vector and back. Now we want to write a quick for loop. And we're going to say const int I in type y. You can't call the for loop on the variant just because of the class reasons. If you created an operator, so if we had like an operator class for like we do in our variant header for like all of these. If we had the same thing for an array, we could possibly do it with an array, but for now I'll keep it this way. And then we'll just print as an integer y at the given index. Now that we've done that, we can also create a vector of type int and call this a vec. And this is going to be set to 1, 2, 3, 4, 5. I'm very creative with my naming solutions. And we're going to do the same thing for this as well, where we just take everything from the vector and just print the item. And once we do that, this will show that all our code's working, and hopefully I don't get any errors when I compile this time. Eat my own word. Small correction that my compiler has just thrown up. This should say int32 because you can't directly typecast the two types because it's not a non-trivial type. It can't stringify or it can't do the operation assignment itself, so we have to do it for it, like so. And that should build without any issues. Now we can just hit F5 to run. Okay, well, I ate my own words. I did get a compiler error, but I know exactly what this compiler error is. And it is something that I neglected to look at because it was pretty important for me to do. So in our operator, in our equals operator, we need to add to our pointer to assign this to be a null pointer. Now, maybe not a good idea to do, given that it's setting it to null, and that could affect other values. And this probably isn't always a great idea to be doing at most instances. But there is a very important reason why we're doing this. This is because in our integers, when we have an integer of type 3, so say we just have in our variant x here, because x is set to 3, the pointer it's pointing to is of a value 0. You know, it's got a 0x0 for how many different numbers, different hexadecimal digits? 3. Which means that it's not a null pointer. It should still be treated like a null pointer and return, but it isn't. So in this case, we need to actually say, okay, well, that should be a null pointer at this point. Let's change that, and that way it won't end up with that whole error that I just had. And hopefully this time it will actually compile, or at least run. Now, if we just run, you'll now see, oh, boom, the code works. You'll notice here, though, that all the numbers read as 0. The reason behind this is because at the moment, because of the freeing problem that I mentioned with x equals y, this array, after it's assigned, considers... Oh, no, dear, sorry. At this point, the array considers, after it's been assigned, to no longer be in use. And therefore, when we get to this part, all of the elements in the array are now nil. So what it does is it ends up looping over and just prints 0, which is what we normally tell it to print when it's looking at returning an integer if it's null. So that's what happens there, and that's just a fault of the code that I've written. Again, this will be something that later on in the series I will address. But the vector side, on the other hand, is working just fine, and it looks like everything there is, you know, it's all good there on that front. And that is, you know, maybe not the most exciting end to the video, but that is actually this topic pretty much all done. So thank you very much for watching this video. I do hope you enjoyed it. I'm very sorry this took a long time to get out. Again, some of those problems I was having with some of my code, that just comes down to me not testing things and not making sure it's actually up to scratch, just sort of throwing together a system based on other things that I'd nicked, rather than actually testing it in a proper environment and making sure it's ready to show. And even then, I've shown that here it's not quite ready, but we will probably be coming back to stuff like ref counted pretty soon, because as this episode alone, this end is highlighted, it's very important to have this dealt with properly. But aside from that, that is, again, I will see you in the next video. The next video, we will be looking at our event system. This is actually something I'm quite looking forward to. It's the class I have designed is not really what I've seen anyone else design, and I'm personally very proud of what I've made. It is, of course, my actually something I can call my own work. And we'll be doing that in the next episode, and then after that, we will be looking at the platform and OS layer. And good news is that the light is at the end of the tunnel. We are very, very soon going to actually start getting a triangle on screen. It is coming close. We are getting there. But yeah, thank you very much for watching, and I'll see you in the next video. Goodbye.